Hello, you're welcome. All right. This is the introduction to thermodynamics. Okay, and we're going to start off with the definition of the term thermodynamics. Now, the word thermodynamics is actually derived from two words. All right. Now, the very first word is thermo, and the other is dynamics. Okay. Now, as you know, thermo is actually means heat, while dynamics simply means motion. Okay, but this is just the combination is a combination of two words, but the actual definition of thermodynamics, okay, is what I'm going to give you here, right? Okay, so thermodynamics, okay, is defined as the branch of science that studies the interconversion interconversion conversion between heat and other forms other forms of energy. Okay, so that interconversion that actually exists between heat and other forms of energy, okay, and that is basically what we study in thermodynamics. Okay, now of course you know that heat is an energy. Okay, before we actually define heat, now look, I want to illustrate what I mean by that. Okay, now heat is an energy, and this heat energy can actually be converted from one form to another. Okay, I hope you still remember the law of conservation of energy. Energy can neither be created nor be destroyed, but can be converted from one form to another. So let me give you a typical example. And of course, please take note, in the process of actually converting heat from one form to another, work is being done. Okay, so that is why thermodynamics, okay, deals with heat, conversion of heat, which actually leads to the doing of work. Now let me illustrate this with a simple. Okay, I'm going to use a simple illustration. Okay, now let's say you have a container. Okay, that has a container that contains air or any form of gas. Right, now this container is airtight with a piston. Okay, it has a piston, okay, that presses on the air, right, because it's inside the container, the air is actually trapped, or there's any form of gas. Okay, now if this container, actually, let's say it's a metal, it can be heated. If you supply heat to this container, now you supply heat, what actually happens, the heat you supply will actually cause the air molecules, okay, or the gas molecule to expand. And by the expansion, okay, what will happen, they will exert pressure on this piston. And what then now happen, the piston will have to actually rise up. Okay, so the piston will have to will move upward against gravity. So which simply means that by the supply of this heat energy, you were able to actually do work which causes the movement of the piston upward. So this simply means that the heat energy, the internal energy, okay, of the gas was converted to the potential energy, which actually leads to the movement of the piston upward. Okay, so in thermodynamics, we are going to be looking at such thing. We're going to be looking at a lot of instances, okay, that has to do with conversion of heat energy to other forms of energy. Okay, but the principal energy here in thermodynamics, all right, the principal energy in thermodynamics is heat. Okay, so I hope that is well understood. Okay, so now let's proceed. So now, heat being the principal energy, okay, in thermodynamics, the question is, what is heat? How do we define heat? All right. Now, heat is the type of energy, all right? It is actually a type of energy that is transferred from hot object to a cold object till the temperature of the two objects, okay, to the temperature of the two objects attains what is known as thermodynamic equilibrium. So um, heat is the type of energy transfer from hot object, please pardon me, hot object to cold object. All right. So to know that heat exists in a body, all right, one of the way to measure the existence of heat in a body is the fact that when you bring that body in contact with a cold body, there's going to be a transfer. Heat will always be transferred from the hot object to the cold object, and such transfer will continue until a state known as thermodynamic equilibrium is actually being attained. Okay, okay, to a state of thermodynamic. Let me write that down. So the transfer of heat from hot objects to cold objects to thermodynamic equilibrium is actually attained. At thermodynamic equilibrium is the point where the temperature of the two uh, objects actually are the same. Okay, so when two of them have the same temperature, we say that thermodynamic equilibrium have been attained. So please actually take note of that. All right. So now we are going to talk about the internal internal energy of a system. So now every system, okay, that can do work contains actually will have internal energy. So now the question is, how do we actually define internal energy? Now by symbol, we use U to represent capital letter U to represent internal energy. Okay. Now internal energy is actually defined as the total sum, the summation of all type of energy. Okay, the summation of all types of energy. So I can actually use um, let me use the symbol. Okay, let me use the symbol small letter U. So the summation of all the energy. Okay, the summation all type of energy. Okay, of all the molecules of the system. Okay, so now let's look at a system that contains gas molecules. Okay, now that system can actually contain thousands, millions of gas molecules. Now each of the gas molecule have energy, and that energy can be of different types. Okay, so as the definition is not just one type of energy, all types of energy that is present. And that type of energy, you're not summoning just all types of energy, you're summoning all the types of energy for all the molecules. Okay. So invariably, there is this a single molecule, there's this tendency that a single molecule might have different forms of energy. Okay. So let's look at the forms. A single molecule might have translational kinetic energy. Okay, translational kinetic energy. Now, if we are dealing with gases, okay, you know very well that the translational kinetic uh, okay, energy, of course, the word translation means movement in a straight line. Okay, so that means the motion of that particular molecule in a straight line actually offers it translational kinetic energy. All right, number one, number two. All right, okay, so please pardon me. All right, so here we go. So number two, you can also have uh, okay, apart from translational movement of molecules, okay, molecule in a container, gas or specifically gaseous molecule can also exhibit, um, they can also exhibit rotational. So, so that rotational can also offer them another form of kinetic energy, rotational kinetic energy. Then it can also be uh, in form of vibrational, okay, vibrational kinetic energy. So vibrational kinetic energy, of course, if it is vibrational, you know very well that okay, if it is vibrational, you know it is it's simply an oscillatory motion. That means the movement of that molecule is oscillatory in nature. Okay, so now, so gas molecules can actually have this type of energy. So now, if we sum this type of energy, some might have just one, some might have a gas can have three of them, might have one. Okay, but if we sum all this type of energy for all the gases, all the gas molecules in a system, all right, in a system, that will give you total internal energy, not just for the gas molecule, because it's not just gas molecules that have internal energy. Um, Liquid can also have internal energy if their temperature is actually, the, it absorbs heat. Okay, solid can also have energy, but they, okay, solid particles can also have energy if they absorb heat. So invariable internal energy, okay, can be for any system. All right, so now with what we have now, okay, so the question is, how do we calculate this internal energy? All right, so we're going to look at some case scenarios. Okay, now our case study here is we are looking at gas molecules. So now looking at gas molecules, and the type of gas molecules we are going to consider, okay, is monoatomic gas. Monoatomic. Now, a monoatomic gas, as the name implies, is a gas that, okay, that is made up of just one atom, one type of atom. All right. Um, Now, if there is such gas actually exists, most gases are actually they are diatomic. But for the case of the for formula, okay, and of course calculation purposes, we actually gonna take, okay, a case where we'll have a system that just contain um uh, monatomic gas. Okay, so that simply means that let's say you got a container. All right, now this container contain, okay, monatomic gas molecules. All right, so now, since it's a monatomic gas molecule, so we expect each of the molecules to have energy. Okay, so now the internal energy of the system now is going to be the sum of their individual translational. So if it is monatomic, okay, for a monatomic gas, okay, gas with for gas with just one atom, all right, what they have, each atom possesses the translational, okay, translational kinetic energy. Each atom possesses translational kinetic energy, okay, because according to gas laws, you know very well that this gas molecules, okay, for individual gas molecules, will actually move in a straight line, colliding with each other with the walls of the container. So their movement is actually considered to be in a straight line, okay, each of them, all right, straight line colliding with each other and with the walls of their container. So now, so for the total energy, now if I want to calculate the internal energy, okay, it's going to be, let's me use K to represent, okay, the their translational kinetic energy. Okay, let me use. So if you have different molecules, right? You can just sum it up to have K1 plus K2 plus K3. Okay, depending on the number of molecules you have. Okay, so dot 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 to Kn. All right. Now, since they are monatomic and they have the same kinetic energy, okay, so I can actually write the formula. This their total internal energy is going to be the number of molecules, okay, in that container, then multiply by the translational kinetic energy of one. Okay, please let me write that. I'm using capital letter. Please pardon me. All right, so the number of molecules multiplied by the translation kinetic energy of one. Okay, so let's say what you have is let's say 1,000 molecules. Okay, so in that case, what you're going to have is 1,000 multiplied by the K kinetic translational kinetic energy of one. Okay, so I hope that is well understood. Okay, so let's actually proceed. So now we're going to actually derive formula for this. Okay, so now U is giving us Nk. Okay, now kinetic energy, translational kinetic energy is giving us, of course, you know, okay, in mechanics is giving us half mv square. Okay, now since we are dealing with gases, okay, we are going to actually write the formula in terms of the molecules of gas. Okay, so it's also equal to 3 kT then divided by 2. Of course, you know what on this, okay, you know that m represents mass, v represents velocity, but I'm interested, okay, with the second part, the last part of the equation. Okay, so that k, this is capital letter K, please pardon me. So this small letter k that I have at the other side, okay, is a constant known as Boltzmann constant. All right. So of course, if you are being given question, you will be actually be given this constant that you know very well that the capital letter T is absolute temperature. That's temperature in Kelvin, absolute temperature. All right. Okay. So those are the two parameters. So now it happens that Boltzmann constant K, small letter K, is equal to universal gas constant then divided by okay, the number of atoms in 1 mole. Okay, the number of atoms, that is Avogadro's constant. Number of atoms in just 1 mole of a gas, okay, or 1 mole of any substance. That's what this N represents. Okay, I can put that in capital. Number of atoms in 1 mole of a gas. So that is what this K Boltzmann constant is equal to universal gas constant, right? Divided by the number of atoms in 1 mole of a gas, or you call it Avogadro's constant. Okay, of course, you know very well that Avogadro's constant, you know very well that Avogadro's constant is constant is 6.02 times 10 to the power 23. Okay. Okay, but that's just by the way. Right. So now what I'm going to do is this. So with what I have here now, I can now rewrite the formula. So I can now write my formula of um, translational kinetic energy, K, capital letter K, to be equal to 3 multiplied by K, which of course is R all over NA. Okay. Now there's something I actually missed from this. Okay. Okay. R plus N, please pardon me. That's going to be R all over NA. Okay. Then multiply by T. So now let's actually use this now. Let's now bring it to our equation for the total, the internal energy of the system. So knowing that K, okay, is equal to 3RT all over NA. So the internal energy of the system now, remember it is actually N K. So that's going to be equal to N multiplied by K, which of course is 3RT, then all over NA. Okay. So now, of course, I believe that in chemistry, you know very well that the ratio, the number of particles or number of molecules divided by Avogadro's constant, right? That is the number of particles in just one molecule. This N here represents the number of molecules, the total number of molecules in that system, and it represents the number of molecule in just one mole. Okay, so this particular ratio, of course, I'm very pretty sure, okay, you must have encountered it before. It's equivalent to the number of moles. Number of moles. Okay, so we use small letter n to represent that. So invariably now, so if you are to now write the formula of the internal energy of a system, okay, putting this into this, okay, n all over n is smaller, and so we can actually write that this way, okay, 3n. So I have to bring the n in front of 3n rt, okay, all over. Something is actually missing, please pardon me. Something is missing. Two is missing. Okay, I forgot to actually add 2 when I substituted for K, please. Okay, I miss out 2. All right, pardon me for that mistake. Then all over 2. Okay, so please take note of the formula. Now this formula is very important. So if you are being asked to calculate the internal energy of a system, okay, of ideal gas, we use the formula 3 and RT then divided by 2. So I hope that is well understood. Okay. Now let's look at a situation. Okay, I will still bring an example, right? But just take note of this formula. Okay, take note of the formula. Now let's look at the units. Since we are actually talking about energy. Okay, let's look at the unit for energy. Now I know that you are very familiar with Joule being the unit of energy. This one is a very common unit, but at the other unit of energy, okay. Now we have energy is measured in calories. Okay. Now there are 2 calories. We have the one with capital letter C, and we have the one with small letter c. What is the difference between the two? Okay. So I'm going to define them one after the other. So I'll start with the one of small letter, calories. Okay. Now, 1 calorie of energy is defined as the energy, the heat energy. Okay. 1 calorie of heat energy is defined as the heat energy required to raise the temperature. All right. To raise the temperature of 1 grams 1 gram of a substance by 1 degree Celsius. So that energy that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius, that's what we call 1 calorie. Now, how is it different from the one of capital letter? Okay, calorie. So 1 calorie, capital letter C. Okay, this time around is defined. This is the energy, the heat energy, the heat energy required to okay, to raise the temperature of 1 gram of a substance, of 1 kilogram, please pardon me. Okay, to raise the temperature of 1 kilogram. So the difference is just this one is gram and the second is 1 kilogram. 1 kilogram, okay, of a substance by 1 degree Celsius. So the difference between the small letter and the capital letter is just 1 kilogram. So we simply means that if you want to convert it, all right. So if you want to convert calorie, we can simply create a relationship. 1 calorie is equal to 1,000. Of course, you know very well that 1 kilogram makes 1,000 grams. Okay, so that simply means 1 calorie, capital letter C, okay, makes 1,000 calories, small letter C. So please take note of that. So now, how does that? Since we are familiar with using joule, okay, to express it, so uh, as the unit for energy, okay, this is the common unit for energy, and of course, when you want to calculate the work done, okay, the energy you will definitely need should be in joule. So how do we convert that, right? So let's see how we convert that. One, to convert from calories to joule, okay, so 1 joule is going to be equal to 4.182 approximately, okay, if I'm not mistaken. 4.182 calories, right? So if you want to just convert calories to joules, okay, the small letter, please take note of this. The small letter, just multiply by 4.182 and you're able to convert it to joule. Now let's look at a typical example. Okay, so let's look at a typical example. Okay, so let's say that a man stores 1 calorie of energy, capital letter. Okay, so 1 calorie of energy stored by a man. Man, okay, let's say of mass 100 grams. Okay, so now if this man stores this energy, okay, through feeding, then he needs to expend this energy. Okay, so the question is, okay, what height, okay, please pardon me, what height of stairs can he climb? Okay, using this available energy. Of course, you know very well that if you want to calculate this now, you know that there's going to be a conversion, okay, of the heat energy to potential energy for the man to actually climb. So in this case, now we are dealing with a conversion of heat energy to potential energy. Okay, so that means invariably the energy, the internal, let me use this, the total internal energy of the man, okay, definitely will be converted to potential energy of actually rising, okay, to a height. But one thing you need to understand is that the energy, okay, it's in calorie. So I have to convert it to joule, okay. So now, first of all, I have to convert the calorie, the 1 calorie, right, to 1000 calories, small letter. Okay, so in that case, now the energy will now be 4.182 times. I need to convert this to, I need to convert it to joule, okay. So that's going to be 4.02 multiplied by the number of calories. So invariably, you just have 4182 joule. So with 4182 joule, now we can equate this going to be 4182 is equal to the mass of the man, which is 100. Convert the 100 grams to kilograms, divide by 1000, that's going to be 0.1. Multiply by the acceleration to gravity, which is 10. Then, of course, that's the height the man can actually climb. So now to get the height, now I'm going to have 4182 then divided by 1. Okay, so invariably this man will be able to climb 4182 meter of stairs, okay, with this stored amount of energy. Okay, so I hope that is well understood, and we're going to look at some other from land example in the next video. Okay, so see you in the next video. Thank you very much.